So what I'm going to talk about today is RHadoop for building and analyzing patient timelines. I'm Saar Golde. I'm the head of the data science team at Knowledgent, which is an information and analytics consulting shop right here in New York. So I'll start with the big buzzword, big data, and how big data is used in pharma research. And there's a lot of different types of big data in pharma research. Some of them are genomic data and stuff like that. But we'll talk about real-world evidence, which is, it's called either real-world evidence or observational evidence. And this is everything that's not clinical trials. So if you run a clinical trial, you control everything, or the pharma company controls most of it. And it's easy to analyze because they kind of play with some levers and they see what the outputs are. But when you look at real-world evidence, it's observational. You can't really discern causality. But it has some additional complications. So it's basically, it's mostly used on based on medical claims. So inpatient interactions, outpatient interactions, prescriptions, lab results, stuff like that. You can go and look at patients' medical charts. Sometimes it's anonymized for HIPAA purposes and stuff like that. And the main goal is to see how drugs are actually used in the real world. So a clinical trial is very controlled but is limited in size. Sometimes you want to see, if people are, or if doctors and patients are actually following clinical guidelines. In other cases, you want to see if there are any adverse events or things like that. You also want to see commercial things like how is my drug doing against the competition? And maybe I can write a paper about how when people use my drug, their spending on healthcare goes down, their outcomes get better, occurrence of other things is improving. So, so for this, companies buy anonymized claims or anonymized medical charts. And there are some interesting characteristics. So the size, it's pretty big. A lot of people say, big data is something. It's pretty big. Whether it's structured or unstructured, that depends. If you buy medical records, they're mostly unstructured. If you look at medical claims, they're very structured. The purpose is either medical care, billing, or operational. The purpose is never actually research, which is a problem because then whatever you want to have in the actual data is not really there. And it usually has quality issues. So there's missing data, there's wrong data. Some of it is a data problem. Some of it is just doctors making mistakes when they code. Some of it is the medical coders making mistakes when they miscode what doctors wrote in the chart, stuff like that. So when you analyze it, there's like two types, right? One is technical. It's big data. It's not really big, but if you think about, so specifically the example I'm going to show here, we had 7.5 million patients. We had 5 million interactions between patients and kind of providers. 5 billion interactions over a period of 5 years. Is it too big to hold in a database, in a normal database? Not really, but it becomes kind of annoying. So one of the definitions of big data is that it's too annoying to deal with the tools you use, and this is definitely too annoying to deal with most of the tools I had. It has an inconvenient structure, so it's a billing structure. So every interaction has a few different diagnoses, a few different procedures. It's spread over many different tables. EMRs are even worse, but specifically we can skip that. And the data, of course, is messy, and a lot of it is missing. So it's missing because of all sorts of reasons. Sometimes it's because of HIPAA privacy limitations, so you don't have people's date of birth, for example. Sometimes it's missing just because it's missing. This comes from medical claims, and they just miss stuff. Claims come late. They don't have the right coding on it, stuff like that. So that's kind of a technical problem. The conceptual problem is that not everything you care about is actually reflected as a data element. So for example, some conditions, when they get coded for billing purposes, you lose a lot of information. So not every condition has a diagnosis code. Remitting relapsing MS has the same code as primary progressive MS. There are 4 types of MS and only one MS, multiple sclerosis, only one MS ICD-9 code. So it's a big problem to separate between those. And the line of treatment, which is what pharmaceuticals usually care about, the line of treatment could be a combination of several different procedures and drugs and stuff like that. So, so the conceptual problem is kind of trying to take the data you have, which is just a set of diagnosis, procedures, claims, stuff like that, and figure out from it what actually happened to the patient, and then from that, try to figure out if you can say that people who did this treatment, which is more than just one procedure, had different outcomes than other people. So the typical solution is that you use some business rules to translate this data to some events. I guess that's it's fairly straightforward. But if you think about, for example, newly diagnosed Crohn's disease patient, right? You use, so the usual definition is 1 inpatient diagnosis or 2 outpatient diagnosis of Crohn's disease, and that's like a long list of ICD-9 codes. You have 1 or more Crohn's disease treatments, so you need a long list of what treatments are used there. You want to, if it's a newly diagnosed, you want to make sure that they're newly diagnosed. You never see a claim saying this is the first claim. So you want to see a washout period of about 6 months before. Sometimes it's a year. You want to actually follow up on them for at least 12 months. So all of those things, they are kind of addressing the different parts, the different complications, right? So for example, you need 2 outpatient diagnoses because people miscode. They miscode less in inpatient settings. So sometimes you'll just see like kind of a random code showing up. So that kind of addresses some parts of the data quality problems. It addresses some parts of the conceptual challenge, right? A newly diagnosed newly diagnosed Crohn's disease patient is something very specific, but if we think about how it represents in the data, it's actually kind of a very complicated thing. And that creates a new problem, mostly that this becomes very sensitive to the definitions of the rules, right? What if I choose 185 days instead of 6 months? Will it change my results a lot? What if I miscoded something? So we want to make sure that that actually works, and since the classic implementation is usually database-based, right? So if you think about all of this translated into a query, right, it's going to be a horrible query because every event is a list of ORs because multiple columns represent the same data. You might have diagnosis in 5 different columns. Every event sequence is either a join or even worse, a windowing query or something like that. All of those things, they don't work well in relational database. And even if you are willing to write a query that's this big, it's really hard to then modify it and see what happens if I turn it to 189 days versus 182 days. Since it's big data, the infrastructure becomes expensive. All of those things lead us to having basically kind of the downside of the classic problem where everyone says, you know, data manipulation, which this is all about, data manipulation is 80%, maybe more, 70, 80% of every project. The reality is that after 80% of the project time has passed, someone tells you, you should stop futzing around and you should start actually doing analysis. So by the time you get to the end, you're kind of tired, you don't have time, stuff like that. So we want to solve all of that and allow to actually do things like sensitivity analysis and cool stuff like that. So Hadoop and MapReduce to the rescue. So this is going to be Hadoop in 2 slides, which is very ambitious. So if you know what Hadoop is, you will probably not need it. But if you don't know, it's going to be interesting to figure out if you actually could figure out what Hadoop is from these 2 slides. Hadoop is an open source software project. It has a few components, the Hadoop distributed file system, and MapReduce, which is a compute paradigm for parallel computing that we're going to be using here through R. And it has a whole ecosystem of additional products and services and tools that we don't really care about for now. The history is that it started with Google. They released in 2003 the Google file system paper, and then in 2004 the Google MapReduce paper about how these 2 work together, the compute paradigm and file system. Adopted by Yahoo in 2009, Yahoo made it open source, and the important parts of everything in it is that you have a distributed file system with cheap storage on computer clusters. You have a compute paradigm that abstracts a lot of the parallelism. If you've ever written parallelized code and you know that you have to start like managing memory, moving data around, processes, all of that, it abstracts all of that. It allows you to just, if you can break down the logic that you need to do to map and reduce, it takes care of everything else. And the framework basically takes care of resilience and a lot of other things that you have to worry about when you have many computers running in parallel. So this is how it looks in terms of kind of graphics. Your data gets split into many different computers. You run something called a mapper. We'll go exactly how mappers actually tie into what we talked now. You have a mapper emits a key and a value. Hadoop kind of shuffles them around such that each reducer gets a key and all of the associated values, and then kind of emits it, writes it out. So Hadoop basically takes care of everything. All you have to do is just write the blue parts, the mappers, and the reducers. And the nice thing is that everything else is actually fairly complicated. So everything else is complicated, but you don't have to care about it because Hadoop does it. Okay. So, so what we want to do is we want to be able to kind of express complicated logic for selecting patients that follow very specific logic. So for that, the kind of natural thing would be to build specific patient timelines. And for that, we can use Hadoop. We can use MapReduce. Specifically, we have a big implementation using RHadoop and RMR2, the package written by Antonio the Great. So how does it work? So you load the data into HDFS. That's kind of outside the scope of doing it in R. And then what you want to do is reconstruct a patient timeline. And this is actually a textbook MapReduce exercise. The first textbook MapReduce exercise you always see is word count. That is way too easy and not very informative. But this is actually very simple. So the mapper reads a piece of data, for example, some kind of claim. It figures out who it relates to. If the data is structured, it's very easy. It's going to be the patient ID. And it returns two things, a key-value pair. The key is going to be the patient ID. The value is the whole claim, everything in the claim. The reducer gets an input, a key, and a list of all of the values associated with that key. In this case, we have a key, which is a patient ID, and all of the values, which are all of the claims about the patient. We can just organize them, and we're done. We have everything we know about the patient in one place. We don't need joins. We don't need anything complicated. We have everything, and since we have it in R, we can just write our logic for it. We can sequence the timing events. We can look at overlaps between things. From now on, everything is fairly nice and simple, and it's in one place. In terms of how it actually looks, so imagine two different types of claims tables, and there's a reason why it's all kind of small. This is the Borat solution for big data. Use a big screen and a small font, but it doesn't actually work because we have billions of rows going down. So what we're going to do is the mapper is just basically going to identify the patient ID for each and every one of them, and it could be different tables of different formats. Hadoop magic happens in the middle, the shuffle sort phase. And what you get at the end as the reducer is you get a patient and all of the record. And the nice thing is you get it in R, so you can do whatever you want with it. Specifically in R, it's such a textbook case that basically running this process is, well, it's about 30 lines of code because I have a lot of spaces in between, but really is one line of code in the reducer and one line of code in the mapper, which is why I think it's the textbook case used for Hadoop. For RMR. So back to analyzing specifically patient timelines. Once we've done, the nice thing is that we've done it in R, so everything is actually in R. What we can do within, when we look within a patient, we can look at the prescriptions, for example, and see overlaps. So we have kind of a graph where you can see that this patient is actually fairly adherent, and they take their meds on time, and at least, well, it's all claims. We don't know when they take it. It's important to interpret it right. But they buy their medication on a fairly regular basis with not too big gaps for the most part. The red part is when they had kind of double dose, or they bought the prescription before it ended, stuff like that. So once you have it all in one place, you can start doing things like that. You can figure out adherence, and you can calculate it, and it's way easier than doing it in anything else. Specifically for diagnosis, you can just take a look. The horizontal axis is time. The vertical axis is different types of diagnosis. Specifically here, you can see this patient has something, right? By the way, this is all done in R charts as a Shiny app. So the output is that you can actually just figure out the patient you want to look at, and you see everything about the patient. But this patient obviously has something because every treatment they have has the same kind of diagnosis over time. At some point, they had something which is related to this drug that they took. But again, it's really important to just have all of this data in the same place so that you can start analyzing it in a meaningful way. Now that the patient information is in place, we can visualize it like you just saw. We can run rules to identify patients belonging to specific cohorts, specific groups. We can run analysis on all of the patient history. So we can look at comorbidities, co-medication, health resource utilization, drug adherence. All of that is fairly easy and becomes, right, you have everything about the patient in one place, so it's a map-only job, basically, right? You just write your mapper in R, you have a list of all of their things, and it happens. It's in Hadoop, so it speeds up you can speed up the computation by just adding another node to the cluster. And since there's no complicated joins on a regular basis, you only have to build the patient timeline once. Once you've built it, all you need to do if you need more speed is just to add more nodes. Or write your code a little bit more efficient, but it really just does linearly scale up because there are no more joins and no more anything. Since it's fast, you can just run way more of it. You can run it many times. You can run many types of analysis. You can start doing sensitivity analysis. You can start doing simulations to quantify the effects of bad quality of data, which is actually really important because it's something that you don't see in the literature almost at all. And the nice thing is that it's in R. So the full power of R is at the tip of your mappers and reducers. So if you have a training set where you don't want to define things necessarily as strict rules, you have a training set saying, this patient record looks like someone with this condition. You can train classifiers and all of that. You can do stuff that's way nicer and more elaborate than just implement rules in a language that's convenient to write and we all like. And if you have small outputs, you can easily just read it into R and do other things in it. So we have 3 more minutes. We'll go over one last thing. So a big thing about analyzing real-world evidence is looking at treatment pathways. What's a treatment pathway? Treatment pathways is like looking at what's the first treatment that the patient gets, what the second treatment that the patient gets, stuff like that. Which building in MapReduce is another kind of real simple textbook example. So an individual patient timeline, it already exists. It's in Hadoop. We can go and analyze them. In this case, the mapper will read a single patient the whole timeline. It will identify what's the first line of therapy, second line of therapy, all of those things, which could be very elaborate, right? Because the first line of therapy could be one of a set of procedures and diagnosis and maybe drugs, and drugs appear as procedures if they're given by injection and stuff like that. So you can do all of that, but again, you have to do it just within a single patient. Then you return a key-value pair. The key is going to be just the sequence of lines of therapy. Therapy A, therapy B, therapy C. The value is 1 because I had one patient. The reducer, as an input, gets the sequence of lines of therapy and a value 1 for each patient that actually had that line of therapy. The calculation is count them, which is just sum it all up. You return a key-value treatment pathway, which is just the sequence of treatments, and the count of patients who went through it. If you want to write a combiner, the reducer is just going to be the sum instead of the count, and then everything works as a combiner as well. I don't actually have it in R, but this is, at least the reducer is at 1 line here as well. The mapper is potentially, or not potentially, the mappers do end up being big because identifying lines of treatment is something that you can, that actually is pretty annoying. And then you can take all of that and build actual treatment pathways, which is, in this case, treatment pathways for Crohn's disease patients. You can see that the big, and it's done in R charts. In Shiny, we actually have a Shiny app. So instead of talking about the Shiny app, I have another minute. Let's see if we can actually get it done in a minute. We have a Shiny app that says, that takes the output of all of that. So we have in our pediatric cohort about 5,200 patients. Out of them, about 2,100, their first line of therapy for Crohn's disease is corticosteroids. The biggest group out of those get immunosuppressants and stuff like that. And since it's a Shiny app and we made sure to keep a little bit more information than just the total counts, we can just look at subsets, hit go, and we get different counts, right? So these are the younger patients, only 1,200 of them. Only 1,200 of them, and the treatment pathways change a little bit. We can exclude some of the drugs and kind of rerun it and see how it changes. So the nice thing about, so that's that. So just kind of to recap everything. So some Hadoop functionality, specifically like MapReduce is perfectly suited for building patient timelines, which makes all of this analysis very, very easy. You can use MapReduce to create patient timelines. You can use map functions only to calculate patient metrics, complex events, stuff like that. MapReduce to build treatment pathways. It's cheap, it's scalable, and our integration allows you to do basically everything with it. And I'm on time, I think.